Hi, my name is Tuyet Vu. Here's my red ID. So we're given this diagram and we're asked to find the principal stresses and the shear max. So to do that, first we need to make a cut at point A in order to find the reaction and the moment of X, Y, and Z. So first I'm going to make a cut at A. I already drew out the diagram. So A is going to be right here. And we're given the axis. So right here is reaction Y, reaction X, and reaction Z. And we also have a moment of Y right here, a moment of X, and moment in Z. We also have the same force apply at the same location as up here. I'm going to convert this to Newton instead of K-Newton. And right here is 500 Newton. So next, I'm gonna make a diagram of to find how the beam is behaving. So I have the R direction, which is just the location of each vector. And then we also have the force and then the moment. Each of them we have I, J, K, I, J, K, I, J, K. I'm gonna do the load. So first, the 750 Newton load at I. So when I look up here because it has the distance which I'm gonna mean. So first load of 750, which is right here. So it's 180 millimeter. And then we also have 16 and 0 in the Z direction. And then next, I'm gonna do the force. So in the X direction, 0, since it's going down, negative 750 Newton. In the J direction, and in the K, nothing. So next is the 500 Newton load. So right here, so we have 220 milliliter. And then in the J direction, we have 0 and also 0 in the K. So next, the force. So we have 0 in the X, 0 in the J. And since it's going this way, it's going to be a positive Z direction, which is K, 500. Next, we're going to do the 10,000 Newton load. So the 10,000 Newton load. So it can be the same I direction, 220. In the J direction, it's 0. It's also 0 in the K direction. So next is the force. So we have it just going this way, which is the Y, the I direction. So we have 10,000, positive 10,000, 0, 0. So next, moment. So a moment is just taking the cost, just R cos F, and the unit for that will be in Newton meter. So I will be 0. This will also be 0. So negative 135, 0, and this will be negative 110. This will be 0. Oh. And down here, it will be all 0. And that is our table for the load, for the R, F, and M moment. So next, we're gonna find the reaction in X, reaction in Y, and reaction in Z, and the moment in X, the moment in Y, and the moment in Z. So to find this, you just need to use equilibrium. So first, the reaction. Well, look over here. For the reaction, because this is a positive 10,000, for it to be equilibrium, it needs to be negative 10,000. Same thing for the J. Because it's a negative 7,500, it's a positive 7,500 to be equilibrium, and this negative 500. Same thing for the moment. For the moment, we have 0 in the X. For the moment in Y, we have a negative 10,000, 110. So it's a positive 110. And this will be positive 135. So from this, since the moment in X is equal to 0, we know that there is no longitudinal moment, so there is no torsion because of the mx equals 0. So next, we're going to try to find the stress by using the angle view diagram and the stress and the shear formula. So I'm just going to do them in order. First, I have, so first we're going to try to find the longitudinal axis, longitudinal direction. So Rx is the longitudinal direction because of this. Because it's going this way, it's a longitudinal. So first, so longitudinal, so 1 or x, that's the axial. So to draw the angle view, we can look from either the lateral direction, from neither lateral direction. So I'm just gonna look at it from the XZ direction. So right here is our X, going down is the Z, and right here is A. So since it's a negative 10,000, since this is a positive X direction, so the negative 10,000 have to go this way. So to find the stress in X is negative P over A. P is just positive 10,000 because we have a negative 10,000, so negative, negative cancel. And for the area, it's just 60 times 32 millimeter. And in the end, I calculated beforehand, we get 5.21 megapascal. So I'm just going to draw all the stress block into the same page so then I can combine them later on. So for the Rx, which is our axial, we have our X, Y, Z, X, and Z, Y. So we just have the X direction for the stress. It's gonna be positive, so it's gonna go, it's in tangent, so it's gonna go like that. And that would be 5.21 megapascal, 5.21 megapascal. Put this aside. Next, I'm going to do the reaction in Y, which is the transverse shear. So for the angle view, we can look from the lateral direction. The force is not acting on. So it's going to look like this with our Y direction going here and our positive X direction, and our A is going to be at the corner. And we have 75 Newton. So the formula for the shear in Y is VQ over IT. So first we want to find the Q. Q is equal to Y prime bar times A prime. So looking at this, we know A is right here. For this, the Q formula, A is the outermost area. Since A is right here, the outermost area for this is equal to 0. Because A is the location of point A. So because of that, we know shear for the R, Y is equal to 0. For the stress block, there will be nothing for RY. Again, because the outermost area is equal to 0, therefore shear for our reaction in Y is 0. So next, reaction in V, which is transverse shear. Same thing for the angle view, we can look from the lateral direction in which the force is not acting on. So positive X going down is direct Z, and we also have 500 Newton. So same formula, equal VQIT. So I'm going to find the inertia, polar moment of inertia first, which is just 112 base height cube. So I'm just gonna plug in the value. So I112. So the base for this is 0.032. The height is 0.06 cubed, and it's equal to 5.76 times 10 to the negative 7 m4 to the 4th. So we know I, we know T because it's just the thickness. V is just what the active force is equal to. So next we have to find Q. So we're gonna, easier for me to look at it from the end view. So that's the end view. This is the neutral axis. Right here is where A is. And from that, we know this is equal to 0.06 from the diagram. And this is equal to 0.32. So Q is equal to y bar prime and a prime. Y bar is the distance from NA to the centroid. Y prime bar. So to find y prime, it's just you take this distance, divide by 2, which you will get the distance from here to here, but that's not what y prime is. The y prime is half of that. So half of 0.06 is 0.03, and half of that, and we're going to take it and divide by 2 to get y prime divided by 2. And next it's just based in the height, which is just that 0.06 and 0.032. And we will get 1.44 times 10 to the negative 5 meter cubed. So next, we know I cube, we know T, and we know V. So now we can plug everything in. We're gonna have 500 Newton, 1.44 times 10 to the negative 5 to the cube, all over 5.76 times 10 to the negative 7 to the 4th. And just the thickness is just this 0.032. And we will get 390,625 or 0.391 megapascal. Since we've been doing the block diagram in megapascal, just convert to that. So next, the stress block for RZ, which is the transverse shear. So transverse and shear, since it's positive, and 0.391 megapascal. Next, we're gonna do the moment of y. It's gonna be a bending moment. Since it's the latitudinal axis. So for the angle view, when I look down from the axis, the axis moment that is acting on. So it looks like that. And positive x direction and z. Now we also have a positive moment, so it's going to go that way. Positive 10,000, 110 Newton meter in moment. And our A is going to be right at the neutral axis. So the formula here is my over I. So we know y is equal to 0 because point A is on the neutral axis. So that's why it's equal to 0. Therefore, stress in x for the bending moment of y is equal to 0. There's nothing to draw for the bending diagram, so I won't go to that page. So last, the moment of z. It's going to be a bending moment. So the formula we're going to use is the same one. Y over the inertia I. So we know m, which is 135 n Newton meter, and y is 0.016. Oh, I forgot to do I. So I is equal to 1 over 12 times 0.06, since that's the height on a cubit, times 0.032 So I'm gonna plug I into here. So in the end, stress in x is equal to a positive 13.18 megapascal. So I'm gonna go back to my stress block. So far we have our x, our z, and lastly we have the moment z. So since it's positive, I'm gonna go that way. 18.3 18.18. I mean 13.18. 13.18 megapascal. So next, I'm going to combine everything. We have nothing right here, so I'm just going to ignore that plane, the zx plane. So for the x, y plane, we only have 13.18 megapascal. And for the xz plane, we're gonna have, so we have two tension stress, so we're gonna combine them, and that will be equal to 18.139 megapascal in the x direction. And we also have a shear stress of 0.391 megapascal. So from just looking at the xz plane, because we have the most component there, it's going to be easier to find the principal stresses and shear max. So from that, we can get stress in x equal to 18.139 megapascal. We have nothing in the z direction, so that would be equal to 0. And shear of xy is equal to 0.391 megapascal. So next, we're gonna find the shear max by using this formula: x subtract z all over 2 square plus xz. So I'll plug everything in. We have 18.39 subtract 0 over 2 square plus 0.391 square. That will give us about 9.20 megapascal. And that is our shear max. So to find our principal stress, we will use a similar formula to that. It's just x plus z over 2 plus or minus shear max, the shear max. So plugging in everything, we get 18.39 plus 0 over 2 plus or minus 9.20. So in the end, we get 9.195 plus or minus 9.20. So from that, we get principal stress of 18.395 megapascal and negative 0.005 megapascal, and shear max, which we already found, 9.20 megapascal. And that is it.